Hello, in this video, what we're going to do is we're going to start looking at the applications of second-order differential equations. Specifically, we're going to look at the mass spring application, where we're going to play with it and see what happens. The reason for this is that a number of other applications all end up looking exactly the same, using the same equations, and the work that we have when we deal with this application ends up giving us knowledge about a number of other fields within engineering. This one, though, has the advantage that it's very easy for us to understand it. Simply a matter of taking a spring which we attach to a ceiling and attaching at the bottom of it some object, something with a mass. And then you simply pull it or compress it and let go and see what happens. So let's draw it quickly. Here's the ceiling. Here's our spring. Attached to it is an object of mass m. We're going to describe the vertical movement by the x-axis. Some textbooks, in order to make things a little easier to visualize in terms of the usual xy orientation, will have the spring attached to a wall and the object moves in this direction. Obviously doesn't make a difference. The point of rest, the equilibrium point, is going to be x is equal to 0, and the x-axis increases further down. So a positive value of x implies that we are extending the spring, a negative value that we are compressing the spring. Now, when we try to examine the way this thing operates, we find that we have up to 3 forces that behave on it in the simplest sense of what the situation might be. So first of all, we have the restorative force. This is the force that we get from Hooke's law. Hooke's law is the one that says that if I have the spring extended to a value of x, so notice if the value of x is negative, then we're actually compressing it. Then what the spring is going to try to do is to get back to its rest position. And specifically, the force is equal to negative k times x, where k is the spring constant. The other thing that we might have, we generally refer to as damping, friction, dash pot, whatever it is that you might want to refer to it as. It is some force that is slowing down our movement. It is a force which is proportional to the velocity in some way or another. We are going to assume for our case that it is a linear multiplier of the velocity. So it's going to be negative, call it c, times x prime. So both of these, the values that we have are negative. They are both trying to bring us towards the rest position. This one in terms of the position itself, this one in terms of slowing down our velocity. And then finally, there could be some external force. Call it f of t. And it does whatever it is that it wants to do. And so we have that in total, the force, which of course is mass times acceleration, which we can write as mass times x double prime. That's going to be equal to negative kx minus cx prime plus f of t. Very quickly, we clean this up. First of all, what we tend to do is to write everything other than the external force. We tend to write it over on the left-hand side. This looks a lot more like the kind of thing that we're used to. This bit over here obviously is not the standard order, so we then go back to it, rearrange it into cx prime plus kx. Now it looks very much like the type of equations that we've already dealt with. a couple of pieces of terminology depend on these two objects. F of t could be equal to 0, it could be non-zero. Same idea with c itself. So when the external force is non-zero, we refer to the motion as forced. When the external force is equal to 0, then we refer to the motion as unforced or free. But keep in mind, the force is a function. So rather than equal, we're going to go with equivalent to, right? So always 0 or occasionally at least non-zero. See over here the friction, the damping. When it's non-zero, we refer to the motion as damped. When it is 0, then we go with a very creative undamped. And now you can pick and choose. We are going to pick and choose free undamped system, and we're going to try to see if we can figure out what that looks like. Now, first of all, before we head off into the mathematics of that, just a very quick connection to other fields. If we take a simple RLC circuit and have it done in the following way, we're going to have a source over here of E volts, and we're going to have a resistor of R ohms and an inductor of L henries, and then finally a capacitor with C farads. Then what we find is that the differential equation that determines this is going to be L times I double prime plus R times I prime plus 1 over C times I is equal to E prime of t, where these three things are also constants, and so it fits exactly this. The conclusions from the one end up giving us the conclusions from the other. So let's go across over there and let's look at a free undamped system, see if we can understand what happens in those cases. We are going to have mx double prime plus kx is equal to 0. So again, free undamped, we tend to refer to this as a simple harmonic motion. And the reasons will be pretty clear right away. What we have is that m and k are both greater than 0. We talked about k already. M better be greater than 0. If you've got negative mass, you've got some problems. And so what we find in terms of the way that we generally do the arithmetic is that it's better to put this in sort of standard form. We divide both sides by m, and this thing over here, once we go into the characteristic equation, it'll be really nice if this was a square. So we define omega naught to be equal to the square root of k over m. It leaves us with something much easier to deal with. And so we have r squared plus omega naught squared is equal to 0. Omega naught squared is definitely going to be positive, so our discriminant is going to be negative. We are going to end up with sines and cosines in our solution, and so we end up with something that looks like x of t is equal to a times cosine of omega naught times t plus b times sine of omega naught times t. All right, the omega naught is going to be what we call the natural frequency of this object, and then we start playing around with it, trying to figure out what it does. Well, there's no friction, there's nothing slowing down the system, and therefore it is something that we can definitely expect over here, that this is going to just show us a free type of oscillation. It's going to keep moving up and down by the same amount, the same quantity, and is going to happily oscillate until the cows come home. So we have something that is infinite in terms of how long it'll keep going before it ever needs to stop. It obviously doesn't need to. But one small issue. When we first look at A cos plus B sine, we expect it to be a little bit erratic. Periodic, maybe, but we expect there to be ups and downs all over the place. And yet, if I take a spring and I pull it down and I let go, it bounces up and down in what looks like a sine wave. So we end up using a little bit of trigonometric identities in order to clean this up. If we take cosine of omega naught times t plus some constant and then expand that, then it'll give us the ability to solve for A and B. And what we get is that this whole thing simplifies into something that looks like just a big constant, occasionally a very ugly one, times cosine of omega naught times t minus gamma. This is referred to as the amplitude phase version of the equation. And the arithmetic is pretty straightforward. It gives us c is equal to root a squared plus b squared. It gives us that tan of gamma is equal to b over a. Be careful over here. Don't just use arctangent, because gamma might end up going in the opposite direction from what it should be. So don't memorize this stuff. Just go over the examples bit by bit. Go over the questions in your textbook. Make sure that you are comfortable with this. You will find, for example, that solving for A and B is very straightforward. When you plug in x of 0, this guy goes away. When you look at x prime of 0, this will have turned into sine of omega naught times t. It will go away, and this one will be pretty straightforward. So the arithmetic is good. It's something which gives us a nice, simple system to analyze. Make sure that you're comfortable with it before you get to the next video.